Yeah, so I'm Sheldon Wasik. I'm the Zone Regulatory Services Coordinator at National Radio Astronomy Observatory. Very, very fancy way of saying I do all of the NRQZ coordination for Green Bank, as well as help oversee some of the Puerto Rico coordination zone that now falls under NRAO for the next, about 2.5 years, as well as other spectrum management problems that show up at the observatory because there's a million of them. So actually, this will probably be one of the only talks here that neglects clutter in a specific way, and I know that oh, and I know that is always a joy to the spectrum world when radio astronomy is in the conversation. So I get it. So a little bit of background: the NRQZ was established in 1958 by the FCC in Iraq. Very, very large box, basically, that's centered around the West Virginia border, 13,000 square miles for those who are interested. So coordination in the NRQZ is basically for all fixed permanent transmitters. So, STAs, mobile, satellite, things like that don't have to coordinate with us, which actually creates some issues for us, but that's not the point of this talk. And we issue concurrence letters for the applicant to then go to the FCC or NTIA for licensing. So we don't license things ourselves. So what is our protection criteria, right? That's always one of the joys in radio astronomy specifically. And to no surprise, radio sources are allowed in the NRQZ. We get a lot of emails, a lot of questions constantly of, why is there no RF anywhere in this 13,000 square mile box? And that's just not true. So our PR person does a great job handling some of those questions. But our protection criteria in general is defined in power flux density limits. In respect to, I'm just going to read it off the slide because I get the numbers all jumbled after looking at these for 3 years. So it's defined as 1% of the system temperature at 0 dBi gain. And the reason why we use the 1% is because 1% increase in system temperature actually requires a 2% increase in observing time to compensate for the increased noise. And 2% is the usual level of acceptable data loss in some of these international rules and regulations behind radio astronomy in general. So that's kind of the history of those. And I will note this now, and I'll note it later again. These limits were presented many, many years ago. And since then, our radio astronomy equipment has just gotten much more sensitive. We now have cooled receivers. These limits are in times of non-cooled receivers, which is kind of alarming to us. Once again, different topic for different day. We also have, much more restrictive limits in RA primary bands. We also have protections for what we call all electrical equipment within 10 miles of GBO, defined in, various stepping out power limits defined under West Virginia state law. Those are not pictured in that graph, but you can just imagine how much more restrictive they would be. Why do we have these really restrictive limits? Radio astronomy is very sensitive. There's no surprise there. We also cover at Green Bank Telescope specifically, or the Green Bank Telescope at the observatory, we cover about 300 megahertz up to about 115, 116 gigahertz. So we cover a wide variety of the spectrum, especially when we start to talk a lot more about these 5G, 6G technologies that are coming out. We're the largest fully steerable telescope in the whole world. We do a wide variety of science from, pulsars, star formations, search for extraterrestrial intelligence has time on our telescope, things of that aspect. We have, very high sensitivity. We can resolve a quarter at 3 miles, as well as some, other miscellaneous stats. We have a lot of users each year, about 600, 6,500 to about 7,000 hours a year on our telescope. And we're quickly adaptable to new science. So what I mean by that is we kind of have a bread and butter science that kind of goes on throughout the years. But if new scientific discoveries need Green Bank to, start to look at a different frequency, or all of a sudden we need to adapt our scheduling out for a little bit, we're very quickly able to adapt for that. And that's one of the great reasons why we have these protections in the NRQZ. And for some context, for those who are interested, we get a lot of applications, and currently I'm the only person who actually looks at these applications in respect to Green Bank. So we get about 650 applications a year, which is a single person reaching out to us. And with those applications, we get, thousands of what we're calling facilities or different technologies, right? You can imagine if, T-Mobile is reaching out to us for coordination, they're coordinating all of their bands at a single site. So that's that number for facilities and technology. About half of these applications are quote unquote fine in respect to NRQZ limits right away. About the other half need additional engineering or additional information, such as a little bit more detailed breakdowns of their antenna patterns or things like that. So as we kind of move into the analysis, we use the GBT as the reference point in respect for the Green Bank Observatory. It sits at about 450 feet tall at its highest receiver peak. And we use all assumptions on a worst case scenario. Now, this next sentence is a little loose, not really true technical terms, but I think it helps illustrate why we look at it in a specific way. So we basically are going to try to underestimate path loss in respect from a transmitter to our receiver. We're not really underestimating, but what we're doing is there's been a lot of great presentations the last couple days of specifically the Google histogram sticks out, right? We are more interested in that 1-2% tail than we are, or on the lower side, whereas someone like a public safety system, if they're trying to guarantee 95% coverage for a county in the area, they might try to overestimate that tail a little bit just so they ensure that they get the coverage. So that's where we're kind of starting our worst case assumptions. And we take the app, and then from that point we take the applicant's transmitter and use things like all of its metrics to figure out how much ERP they have in our direction. So the goal, like at the bottom of this picture, is we don't care how much power you're sending away from us, as long as you're meeting the power density on our site. That's mostly what we're worried about. So kind of touching on that analysis again, in principle, we're just comparing the received field, the expected received field to the system that's outputting it in respect to our limits. And after that, we're allowing for some re-engineering after that. And the way that we do that is because no one likes to use propagation models and talk about power flux density limits on site, especially the FCC and NTIA. They like to work in ERP. We just reverse engineer that and give the applicants an ERP that they need to meet in our direction. And obviously, that's where propagation models come in. So we utilize the SoftWrite terrain analysis package, and Todd Summers, who's one of the directors on research and development for SoftWrite, is actually in the panel this afternoon. So I definitely recommend everyone to listen to that or ask Todd for specific questions on the rounded obstacle model, because he's going to be the person that I ask if you just ask me. So sorry, Todd. But yeah, so we use a rounded obstacle model, which is essentially the way that we kind of explain it is a rounded out Longley Rice model. Mostly it comes from the historical aspect that we're treating Appalachia as a very rounded mountainous region compared to the Rockies out here, which are very sharp. And SoftWrite has done some very good documentation in these plots. All credit to SoftWrite. We kind of think about these peaks in a different way than your traditional ITM Longley Rice, where we have the opportunity to skip a peak depending on the wavelength dependence. That's about my knowledge on it. And this is why we sometimes get a little bit less path loss compared to your typical ITM. And I'll go on to show that in a little bit more detail. So additional model parameters, right? We use 10-meter topography data. We're acknowledging that there is more higher resolution data out there, but we've historically tried to keep all of our parameters the same for the last 10 to 20 years, mostly because as someone comes and coordinates with us, 2-3 dB might not seem a lot in the grand scheme of things, but when we're talking to a public safety system or a telecom and we say, you can have 10 watts in our direction, and then all of a sudden they recoordinate 3 years later and we're telling them you can now have 2.5 watts in our direction, we get a lot of backlash for that, believe it or not, and it's not really the most fun. So we try to keep our model parameters the same for that reason. We also use a minimum loss model, which is just your free space plus either your diffraction or troposcatter, whichever is a less loss. And we do everything on just point to point. So you have a transmitter location, height, we just map that straight to our telescope. And once again, I'm I'm acknowledging we don't use any clutter in these because right now we're just trying to be a little more conservative. It seems like there's a lot more unknowns, which is the purpose of this consensus conference, right? Um, but we do acknowledge that it does exist for reason if actually have a pretty good example recently. We have a company around GBO putting in just like a water smart meter reader, and they're operating like 930-ish megahertz right in that band. And we've found some NTIA documentations at that specific frequency for the clutter losses through specific brick buildings. So we've encouraged them to use that type of clutter data for their calculations because it is so well defined in basically what we're going to call legal documentation. So in the aspect of that, we do encourage people to use clutter losses if it is well defined. But for the sake of our propagation models, we aren't using them right away. So why no losses? NRQZ, we can't really get something back that was given up. We could argue with someone based off of coordination and this and that. Not in our best interest. We do also like to interact well with the community. Sometimes that can't be done. But this also helps assist in protections from model errors. There's a lot of deforestation that's kind of happening in Appalachia right now. So that's just one of our pitches as to why we're not doing that. So yeah, kind of bringing it all together, all those points. Basically, if the proposal is going to meet our limits after we run the propagation model and figure out its ERP in our direction, we just grant them a concurrence letter and they run with that to the FCC and NTIA. If not, and we expect to pick up harmful interference, that's defined as above our NRQZ power flux density limits. We're just going to work with the applicant to re-engineer the system or find some of those more specific building losses, like in the case for those water meters. And we eventually do some site inspections around for applications that seem to be more at risk of interference for us. And this is done on a very almost informal basis from one of the employees at Greenbank. So he drives out with a what he calls the RFI truck, and he will measure, what your transmitter height, antenna azimuths as you define them to us. So it's a way for us to just kind of do some cross checks with what's submitted to us. In free time, which sometimes that varies depending on application workloads and whatnot. We're always trying to understand the RF environment, where certain designs can go, even better understand when we are receiving interference, where's that most likely to be coming from. So that's kind of some other stuff that we're doing at the observatory. Right now pictured on the left is actually common cell phone bands at a randomly picked mock site. And the reason why I wanted to plot these out is, so what we're looking at here is so I use ITM Logic, which is just an open sourced ITM software that, propagation losses. I use that with some differing reliability and confidence levels to compare to our rounded obstacle model. And the reason I did that is because as we talk with a lot of different agencies and applicants and RF engineers that's submitting applications to us, we often get a lot of backlash for our models because no one uses it. I think SoftWrite's probably had, 2 or 3 people ever purchase the rounded obstacle model, even though it is there for purchase, and it's not really a thing we're holding on to for that reason. But what I kind of found was the rounded obstacle model pairs up very well with what I'm calling the minimum loss of ITM. So the minimum loss of ITM is, your 1% confidence reliability models, which is the gray bar, and the rounded obstacle is the yellow bar. So there are still differing models, but it's been a way for us to kind of explain what's going on to some of these applicants and the reasoning behind, we are using a worst case scenario for that reason. But it's not so extreme to some of these other propagation models that have been shown to severely underestimate the losses. And then on the right is a coverage map of locations in a county that's around Greenbank where they could put one of the statewide public safety service towers. And the reason why I plotted this out is because we have a lot of, community issues with public safety and safety of life for that reason. Obviously, telecom, commercial industry brings economics, brings communications, but at the end of the day, public safety assists in lives. So we've had some conversations with a couple different agencies, applicants, counties, and tried to fit their public safety systems in and around the Green Bank Observatory and the NRQZ in general. And that's been one of our, more working cases with applicants where we often don't do that. So that's just a prime example of, things can be very restrictive in the NRQZ for better or for worse. So challenges and concerns, right? I mentioned this. We want a good relationship with the community. Public safety, just like I mentioned. Wi-Fi. Wi-Fi is always a joy of a question that we get asked for people moving to Green Bank when that does happen. And long story short, since it is unlicensed, it gets deployed anyways, whether we like it or not. So we have quite a bit of interference at specifically the 2.4 gigahertz band. And that's one of those battles that we kind of have to pick and choose of, if it's 200 meters away from the telescope, direct line of sight, we might care about it a little bit more than 4 miles down the road over a small little ridge at a restaurant that everybody goes to. So that's just one of, those relationship aspects that is tough at times. We don't really understand the aggregate impact at the telescope right now, which is also alarming because as, you saw the numbers as we're getting 650 applicants a year. If they're all looking at, say, 10% of those are looking at similar frequencies and they're all pushing right up against our limit, how does that start to look at the telescope? Everyone's just kind of up in arms because we have to look at things at a site-by-site basis right now. So I'm just going to mention that challenges and concerns. Maybe we'll get some research there eventually. Propagation model variations, kind of one of the reasons why I wanted to compare to that ITM logic, what's often considered as the industry standard. It gives us something to work off of to kind of have those conversations with people. Once you lose a frequency, it's very hard to get it back, which is why we take the conservative approach, and we do tend to care about that 0.1% tail that maybe the general community doesn't, because we are so sensitive. And also, interference not required to coordinate. Satellites, obviously, that's the big one right now. You obviously have airplanes above us at all times, so we see all that interference constantly. And once again, limits for GBO were developed before cooled receivers. We're a lot more sensitive now, so we do pick up even coordinated things that, RF obviously travels in weird ways, so we understand that, but some of the stuff we do pick up is also probably for that sensitivity reason. So yeah, in conclusion, that's how the NRQZ coordination process works. We do allow applicants to re-engineer things. There's thousands, if not tens of thousands, coordinated transmitters all throughout the National Radio Quiet Zone, and we still hold, pretty good core interference protection where we can do the majority of science that we want to do. So we're, constantly using models to understand the RF environment, and yeah, thank you. That's about it.
Any questions? Chris just. I got one look and then I'll
Okay, I'm local, so I have privilege. Thank you. I'm Masood Al Federated Wireless. So yeah, thank you for the citing. One thing that we are eager to see. Everybody knows that these NRQZs, NRAO, and Table Mountain and others, they are one category of incumbents that we protect at the CBRS band. And of course, in some areas, they're limited. And right now, we have criteria for each one. We have different criteria. For example, for Table Mountain, we have different protection level per spectrum, and even the number of channels that are available and we can allocate to users. So we have defined all of them in WinForm documents. It's available. But based on your requirement, we did all of the calculations, assuming only ITM. So no other aspect of clutter or any other propagation models are involved. It's purely ITM. So one question that I have is that whether ITS is looking at potentially revisiting that and allowing us to update, and that would open the, of course, it's not as big as the like DPAs that the one that we saw today, but at least for some customers, it would be helpful if we we can keep the same protection criteria, protection level. We can keep the same methodology that SAS applies to protect the quiet zone. But hopefully, if you can apply like clutter, then that would open up a spectrum for some customers. Over.
Yeah, no, that makes a lot of sense. And we definitely understand the difference between models used here and there. I will also note that in the National Radio Quiet Zone, there's one other facility that does get protection, and that's the Sugar Grove Research Station. Yep, so that's a lot less open of their protection criteria. So I would be curious to hear how Google SAS handles that specifically. Right, right. Yeah, so yeah, we do still get requests, actually quite a bit. I think I actually have one right now that I need to analyze. That is just a typical CBRS request. So they do still trickle in on a application basis, and I guess I feel like there's a lot of weird gray area right now of how CBRS has to coordinate or doesn't have to coordinate with the NRQZ. So yeah, go ahead.
So, sorry, I'm not talking about coordination. So obviously in Part 96 rule, coordination is allowed. So if somebody wants to operate within the premise of quiet zones, yes, they can come to you and coordinate with you, and that coordination can be passed to us, not Google SAS federated ones, and we can manage that. I'm talking about the protection criteria that we need to apply even before any coordination is discussed. So my question to you and the kind of the management and the people who own these quiet zones, that are they willing to discuss and allow us to use a more realistic propagation model for protection, not about coordination? Thank you.
Sure. No, that's a fair question. And yeah, I'll definitely ask some other spectrum managers around, since that's basically 1 or 2 levels above me, but that's a very good point. Thank you.
Hi, Chris Wiesorick with T-Mobile. I am a person who spent a lot of time looking at propagation maps in Pocahontas County, West Virginia. And I'm curious if you've had any interactions with your colleagues and peers at the Federal Communications Commission about build-out requirements around the National Radio Quiet Zone, because we as licensed carriers are required by law to build out around there, but you also want us to not build there,
Right.
bottom line. And it's really, really complicated because, especially Pocahontas County, if you have to build a POPs or geography, the geography are at the Green Bank. And so what on God's green earth are the FCC thinking when they have, 75% of Pocahontas County needs to get the population constructed? Well, then you also want not a single site. You don't want a spark ignition vehicle, for goodness sake.
Yeah, we've, so I guess I'll answer the first part of your question first.
Service for T-Mobile or anyone else, because I'm going to go there next week with my family for vacation.
You're going to lose service about 40 minutes out. Unless you're up near like the Snowshoe area. Snowshoe has some signal over there. But as far as our communications with the FCC, I don't think that's ever happened. As far as, they know we exist. They know we have limits, and they know how we coordinate things. But we've never explicitly had a build-out conversation with the FCC. We've had it with Pocahontas County and with Pendleton County, in Highland, in Bath. And I know all the counties are very eager to get service. And on our side of things, this is why I always brag, we don't license things. We just get to comment on things because ultimately it's the FCC's final decision. But as far as just coverage in the area, we also understand, there may be some more open areas that you guys can deploy in, but that might not hit the population centers. And I think that's the biggest issue, right? So we're actually we're working with one of the T-Mobile engineers right now, Jason Galloway, I think his name is, and he's sending us a couple areas around the West Virginia state specifically, and just having us run some preliminary limits for you guys, so you can maybe see if you can squeak something in here, squeak something in there. Maybe you just have to insanely down tilt in our direction, or something in that aspect. So yeah, I get it. I guess feel free to chat with me after this if you want.
All right, any other questions or online questions? Check online real. We got another minute. All right.
So what's typically the power spectral density that you're scared of? I couldn't see the y-axis.
Oh yeah, so that is dB watts per meter squared per hertz. So it can be kind of where we see, or where I see the biggest issues, is actually where you start to get at the bottom end of that. Basically right around 1 gigahertz, you kind of get at the bottom end of that power flux density limits that we're looking at, but you still get pretty decent propagation out of things. So that's where I see that we have the most objections to when they are actually being deployed. Obviously something like the low band cell stuff is just going to propagate a lot, where we're going to see a lot of issues there. And then the higher ends of the spectrum aren't going to propagate as well. So we don't see as much issues there. So I would probably say between about 600 megahertz to about a gigahertz, we probably object to the most, but that's probably some sort of bias. That's where most of the spectrum lives, that we see coordination applications come in for. If that helps answer your question a little bit.
Okay, cool. Let's I've got one more online, and I think we'll call it there. Because I want to make sure folks online know that we're paying attention. This is from Mahmoud Rahman from Innovation Science and Economic Development. The question is, how does coordination with NGSO satellites take place where power flux density varies? Yeah,
so right away I can say satellites don't have to coordinate with us unless the National Science Foundation has some sort of MOU or something outstanding with that. Most of the time, I'll just use an example right here. Sirius XM blows us out of the water. We see that constantly all day long. But for some of these other satellites that maybe they kind of pick and choose their time a little bit, they often reach out to us, and there's very few, maybe a handful at best. They often reach out to us and tell us when they're going to be using a certain frequency at certain times, and we can sometimes schedule around that, sometimes just eat the interference. It depends a lot on that, but yeah, often it's them reaching out to us for us to understand what to avoid or what to look out for.